Okay, well, I'm Peter from the AARNet Network Engineering Network Architecture team, and I'm here today to talk about AARNet, Australia's academic and research network. Our history starts in 1989 with the establishment of the first internet connection into Australia with a 56 kilobit satellite service from Hawaii to the University of Melbourne. We're owned by 38 universities and the CSIRO, who are our shareholders and our largest customers. We're a not-for-profit company, and we're a licensed telecommunications carrier providing telecommunications, cybersecurity and data and collaboration services to our customers. Like Rhiann's in Craig's talk yesterday, in addition to our shareholders, we provide services to the wider research and education sector in Australia, including schools and TAFEs, research organisations, health and medical research, scientific instruments and public institutions. AARNet is one of 120 research and education networks worldwide. These include Rhiann's in New Zealand, Giant in Europe and the Internet 2 national backbone in the US, among 120 others. AARNet owns or has access to around 25,000 kilometres of fibre optic links across the country through major metropolitan cities and interregional areas. Basically, if there is a university, a supercomputer facility, a particle accelerator, a space telescope or a radio observatory in the desert, it's likely that AARNet has dug up the ground and built a fibre to it. The network is large and operates with a lot of white space or excess capacity. Our biggest customers are also our shareholders, so if a customer has a burst of traffic that nearly fills one of our links, it's not seen as a problem or a case of a missing policer. It's much more likely that we're about to make a press announcement about how great it is. AARNet also operates our own international network, including lease capacity and ownership interests in several submarine cable systems to interconnect Australia's research and education communities to the other 120 research and education networks worldwide. Our network has undergone several generations over the years, starting with what's now called AARNet 1 in 1989, to the current AARNet 5 generation starting in 2023, which is the focus of the remainder of this talk. The first topic that I want to talk about is packet optical integration, and I did have a bit of a panic then when Stephen started talking. I think we're an example of spectrum sharing light inside one company, and the special use, the bonus use case that Stephen mentioned is basically what we're an instance of that I'm about to talk about. AARNet 4, the AARNet 4 network, the current and previous sort of generation in transition to AARNet 5, is an instance of, like many carriers, where there's operated with a separation between the packet and optical networks, even though we're the same company. The IP routers, the packet devices, see the optical network as a provider of nailed up point-to-point circuits, and they use inexpensive short-range optics that transmit a few kilometres or a few hundred metres. The optical network carries the signal hundreds or thousands of kilometres and hides the complexities of optical transmission, such as distance, signal strength and modulation. Now, I did include a couple of slides that are almost certainly redundant here, but I think I'll continue with them for flow. If you do want to learn a bit about optical networking, you can come to AusNOG and listen to Stephen, or there's a presentation by Richard Steenberg, and he's presented at NANOG a couple of times. He has updates it every few years for new technology. I'd highly recommend that talk if you want to learn a lot about optical networking in a 2-hour YouTube video. DWDM, everyone probably already knew that's there. Multiple signals are carried over a single fibre pair as a wavelength or a colour of light. 32 to 96 channels is common, and it's transmitted over very long distances and very high bandwidths. The next component was mentioned before also, transponders, but basically they receive grey signals from the client and they convert them, the client in this case is a router with short-range optics, and the client-facing port on the transponder is Ethernet, but it could also be legacy SDH or other formats. The transponder reads the electrical signals from the client optic and converts it into a DWDM wavelength, one colour. At that point, it's now ready for transmission over the long-haul DWDM system, and the signal's optical, not electrical, all the way to the far end. So what do I mean by that? Well, it's a stream of photons that don't undergo any further optical to optical conversions on the way. The photons go all the way on a long-haul system, say from Melbourne to Sydney, and they don't stop. They're not put into buffers, and at times they are re-energised multiple times by optical amplifiers, but they remain an optical stream for the distance. A muxponder is basically a transponder that combines multiplexer and a transponder to aggregate multiple smaller streams into one OTN container and transmit that as one DWDM wavelength. The next component is a ROADM. Think of this, it's a wavelength switch. So if you think of an Ethernet switch, it switches Ethernet frames. A ROADM is an optical switch that switches optical wavelengths. The O stands for optical because it's an optical signal, not electrical. And as an Ethernet switch has frames come in input ports, and then it switches them out output ports, or perhaps along a trunk to a neighbouring switch. The ROADM controls the addition, add drop, or pass-through of wavelengths. And the key thing is that it's reconfigurable, which allows an operator to remotely and via configuration to determine which signals are added and dropped and passed through. In the picture, if you were to imagine that's a ROADM in Canberra, Melbourne coming in from the left, the purple wavelength is Melbourne to Canberra circuit dropping out on a router in Canberra, and the blue signal is a circuit that's being injected by the transponder from the client router in Canberra on its way to Sydney. And on its way to Sydney, it's going to pass through multiple ROADMs and amplifiers as it goes. Right, so with that covered, let's talk about packet optical convergence. So the basis of this is that we co-locate a router at each of the ROADM sites. We're already at the ROADM site, so we're basically extending the capability of the site. In regional sites, that's a 1 RU router with probably 2 400 gig ports and a couple of 100 gig interfaces. In metro sites, we have larger versions that have around 20 400 gig ports to terminate all the multiple intercap runs coming into the city. Into the 400 gig ports, we install DWDM or coherent optics, and the router is configured to transmit at one specific wavelength, and it connects directly to the ROADM, and the ROADM adds that input signal into the DWDM carrier. These optics are called ZR plus optics, and these are the things that have made possible packet optical integration, as they plug directly into router interfaces and perform the entire function of a transponder, eliminating the need for the transponder. The ZR plus optic has a high launch power, which enables it to get the signal all the way to the destination with the assistance of amplifiers. So that may be a distant city. The green wavelength in my picture is making it from one metro area all the way, say, Melbourne to Sydney. The blue and purple ones are examples where the wavelength is carried only from one ROADM site to the next ROADM site. We call that the milk run because it drops off at every town along the way. So the benefits, I think, are already clear, but the first and obvious one is that we no longer need to buy and maintain transponders, and we get to retire a bunch of end-of-life equipment like our SDH equipment. In regional transmission huts on our intercaps, space and power are obviously very tight. So where a transponder previously occupied one rack unit and used 150 watts, give or take, and there was multiple of them needed, we now install ZR Plus optics, which use about 25 watts, and you can plug multiple of them into the router. So yeah, the 1 RU is already there for the router and replaces multiple transponders. You also get increased network coverage. Every ROADM site now has an access router for customer connections at 1 through to 100 gig on a bank of Ethernet ports, and you can provide basic services originating in all of those sites right across the country. So basic layer 2 E-line, ELAN, and layer 3 VPN services. More difficult services like internet, not difficult, but full routing table, obviously is in the capital city. We haul them as layer 2 E-lines back to the capital city for termination on a higher scale PE. So another benefit is closer to the customer. Consider a scenario of a 1 gig Ethernet point-to-point circuit between two regional campuses that are 30 kilometres apart, but 300 kilometres to the closest capital city. In addition, the customer would also have multiple services there. So in addition to that point-to-point circuit between those two campuses, they'll each have an internet connection which needs to be in the capital city. So because of transponders, we hauled, in the past, we would haul the red and the blue wavelengths back to the capital, carrying the point-to-point and the internet service, and so we could terminate the internet service in the metro. But it also means that the point-to-point circuit between the two towns now has to hairpin through the city, increasing the latency, and it also means that an outage or even planned works in the metro DC means that we have to explain to the customer 300 kilometres away why they're going to experience an outage. In a packet optical situation, the campuses still connect with their same grey optics, but now they can easily choose between 1 through to 100 gig. They can upgrade and change that easily. And the service is built as a point-to-point layer 2 VPN service directly over the MPLS core between those two sites, resulting in optimal switching and latency, and it removes the dependency on the capital city. Protection is another benefit. So in an optical network, protection requires manual configuration to specify a fixed path for the primary service and the backup path. Whereas in a routed network, it's inherent. It's just the MPLS reroute in the shortest path available in the IP routing table with fast reroute and all of those things. But there are cases where sometimes the customer doesn't want the service to be protected. They would rather it go down than experience extra latency, or they might want diverse services. In those cases, we use segment routing, traffic engineering, or SR policies to restrict the rerouting. Okay, so that's that brings me to the second topic, automation. A stated goal from the start of the AARNet 5 project was automation from day one, and we're on track in that regard. All configuration on Greenfield's devices has been deployed through automation, so no human manual config, but we're still working on user interface and workflow systems to drive the network-facing automation, which is probably, possibly harder. The basic unit of our automation is a service. That's a component that delivers one network function, and it's standardised and repeatable. The building blocks that we use to construct our network and to construct the products for our customers. So why standardise? Well, it's not porridge. Similar though. If you follow a process to make a lot of one product, the aim is that you'll make a perfect, consistent product like the muffins on the left. But like baking, everyone has their own tastes and preferences, and particularly for a company like AARNet, where we want to help the customer out, we tailor the solution to the customer's needs, and eventually, standard becomes custom. So how do you make it standardised and repeatable? Well, you expose your product through an order form, and you control the manufacturing, so that's a service. So continuing that baking analogy, but you define a well-defined set of options, but you also define enough options that you've got flexibility to allow for a reasonable number of the customisations, but maybe you weed out some of the outliers. So what are the building blocks for AARNet? You can break it into two categories. There's customer-facing products and services, things like customer access link, a point-to-point Ethernet service, or an internet connection. The other grouping would be infrastructure services, the things that we use to build our fleet of routers, a template for standard device management, or a backbone link, or a routing protocol enabling a routing protocol. The benefits, standard and compliance configuration, and it also means that you now ensure that all of your configuration is consistent with the network design, because it can't really be anything else. A key component of our automation is the role of a service orchestrator. That's a piece of software, and it implements a model-driven approach. By that I mean you define a service, and that's the order form and the manufacturing process. So effectively you implement the order form and the manufacturing process, and you load them into the orchestrator. Then you create instances of the service, and that's basically manufacturing product, and the service config. That's right. So I'm lost. Sorry. Start again. So a user operating a workflow system via a user interface in the picture would create instances of the service. That's handed by an API call to the orchestrator, which translates the service config into device config and deploys the device config to the device or devices needed to deploy that service. But it's also, the other critical role of the service orchestrator is service lifecycle management. So we've just talked about creating services, but it's critical that the orchestrator remembers what it did to deploy that service. So then later in the life of that service, it allows it to be modified. For example, if it was a customer service, they might ask for an upgrade, or AARNet might change our implementation. For example, we might add features to the service type, or we might even re-implement the service to change the protocol that's used behind the scenes to implement that service. So the orchestrator needs to basically assist us in making that transition. If we change the service, redeploy all the services, and the orchestrator will just make the changes. It also allows you to audit services and make sure that they're just still deployed as they were originally, and that they haven't been modified, for example, manually on the router itself. And if we find something's out of sync, you can ask the orchestrator to fix it at the time you ask it, at the time you want it to. And the other thing is something that's often forgotten, but it's important, is decommissioning the service. It's often forgotten, but basically the orchestrator put the config there so it knows also how to decommission it, knows all the parts that have been deployed so it can clean them up. We're using Cisco NSO as our orchestrator, and we're very happy with it. It implements this full service lifecycle management. It's multi-vendor, makes that easy, and every service that you define is immediately available via a RESTconf API interface to our OSS systems. which is how we plan to deploy them. So for all of those create, modify, audit and decommission, they're all available as soon as you define the service. And it's a difficult task, but having a mix of who's the master, whether it's the orchestrator or config on the device, or a mix of both, NSO, I think, is as good at making that possible as that difficult task is. Okay, so getting down to some nuts and bolts. The first step you have to do is to define a service. That's done in a modelling language called Yang. It's developed by the IETF, and it's actually what the vendors are using mostly for defining the syntax of their CLI and the API interfaces to routers. It captures the service's capabilities, all of the options, parameters and the constraints of the service. And it's independent of the vendor of the device. For example, if you're implementing a BGP filter service, you just define the service with no regard to the policy language of the target device that it's going to be implemented on. It's also independent of the device model. For example, if you're using a feature that has to behave differently on the different chipsets of different routers, it's not the role of the service to deal with that. You just want an internet service. And it abstracts away the complexity of building, of configuring the device, and even to the extent like, whether the service, if it's an Ethernet service, whether it's built with a VPLS protocol or eVPN, the service just doesn't want that. It just says I'm a point-to-point Ethernet service. On the right, we've got a sample, very sample Yang model for a service. For just adding management to a device. It just contains a few items highlighted in yellow, and they'll flow through the slides. But basically the device name and a list of syslog servers that it should send its syslogs to. So basically you define the Yang model and you load it into the orchestrator. So now effectively you've got your order form for the service. So the next step is manufacturing, because I keep saying order forms, then manufacturing. The manufacturing is basically done by the template. This is what makes the service standard and repeatable, but it's also what deals with all of those things that I just said before, the vendor differences, the model differences, the protocols, and encodes the implementation of the service into the template. So it's built by network engineers and before the services, made available to the OSS systems. All the values in yellow carry through any device name. If you want to configure the device's host name, it's supplied in the model and it's available to the template. Most things in a template are static. You don't want to have to type in the same things every time you create a service. The template, you put them in the template and they're going to be there and none will be forgotten. Multi-vendor support is dealt with by basically you just put in their tags for as many vendors as you need to implement the service on, and the orchestrator will generate syntax appropriate for the device that it's deploying to, because when the device was registered with the orchestrator, it discovers the device type and vendor. And the logic facilities you expect of a templating language, things like for loops and if statements are available, and you can always call out to Python for complex code that you need to write. Basically anything you can do in a Python standard library, you can add code if you need to. So the last thing is you've loaded the service model and the template into the orchestrator. The next thing is to create instances of that service. So a user in a user interface maybe would be executing a create new router workflow. That allocate resources in inventory, and then the workflow system sends a RESTconf call to the orchestrator, passing through basically values for the items in yellow, which were the things you need to fill in to create an instance of that service. The orchestrator takes the service config, runs it through the template and expands that into device config appropriate to the vendor that it's deploying on and pushes that to the device. And that's the start of the service config management lifecycle for that service, the modify through to decommission. Okay. Stepping away from simulated examples to a real example, take the case of a backbone link. A circuit designer can, in the inventory system, we use NetBox, but basically in your inventory, the designer allocates devices, interfaces, and in IPAM, allocate IP addresses. The workflow orchestrator may have some defaults. It may know which routing protocol is in use for a particular part of the network. It can fill that in, or it might allow the designer to override certain values. But through that design process, it allocates and gathers all of that information unique to this backbone link, which is a bundle with 2 members, packages that into a payload, that's on the left, the payload for the API call, sends it to the orchestrator, and the orchestrator will generate however many 100 lines of device config needed for multiple vendors to enable all those things that I've got written there, like a backbone link that, we run pretty much those things on a typical backbone link. It takes care of all of those. All of the config we know will be compliant, consistent with our design, and no protocol or single line of config will be forgotten because it can't be. Ongoing, if we decide to add a member to the bundle, you go back to inventory, allocate another port, design the cable and rerun the orchestration, and it'll just add the member to the bundle. The orchestrator calculates the minimum differences in config and deploys just that change. If we change our design, for example, some detail of, for example, if we change the interface description format, we'd modify the template and just redeploy all of our existing backbone link services, and they'd all be redeployed. One other example, we connect all our sites with an NTU. These are all the topologies that are possible for those uplinks. Basically, you go into inventory and allocate as many devices and interfaces as you like, run the orchestration, and you can upgrade from a single connection to a dual, a lag of 2 or a multi-homed lag. And lastly, just as one example of how powerful it can get, it was asked, could we migrate an internet service? These aren't live yet, this was in the lab, but a key part is the modelling. We model our internet service as being built on a virtual access circuit, meaning that it's a logical object that specifies the device and interface. If you want to relocate the internet service with potentially IP addresses and BGP neighbours and filters from PE1 to PE2, you go to the virtual access circuit, change which PE it's on, and reorchestrate the internet service. And in our lab, lo and behold, it just picked up all of those components, the interface, filters, everything, and showed signs that it will move it. We're not ready to do that in production, but that's an example where just by changing one field in inventory and reorchestrating, we're able to relocate an internet service and all of that config with it. I'm finished. So thanks to all of the AARNet team working on the AARNet 5 project. Thanks for listening, and any questions if I've got a few seconds left.